This conference will now be recorded.
Very good evening, students. We'll continue discussions on PYQs on the paper JEE Main 31st August 2021 Shift 2. So as I had mentioned yesterday, we'll take up questions from 12th part today. So maximum questions from the 12th part we will be taking up. So the first question here is from moving charges in magnetism. Let us read this and try to solve it. So the question says the magnetic field vector of an electromagnetic wave is B is equal to V0 I plus J by root 2 cos of kz minus omega t, where I and J represents the unit vector along x and y axis respectively. At t is equal to 0 second, two electric charges Q1 of 4 pi coulomb and Q2 of 2 pi coulomb located at 0 0 pi k and 0 0 3 pi k respectively have the same velocity of 0.5 c I cap, where c is the speed of light. The ratio of the force acting on Q1 charge and Q2 charge is how much? So we have to basically find out the magnetic force. Okay, so we know magnetic force FB will be is equal to Q into V vector cross B vector. Okay, so all the things are given. Q is given, V is given. What else we needed? Okay, so let us find out what is the force on the charge Q1. Let me write that as F1. So Q1 is 4 pi coulomb. So let me write this charge 4 pi. V is 0.5 c I cap cross B is B0 I plus j cap by square root of 2 cos of kz. I'll write the coordinate of the charge Q1 in place of z. So k into z is, this is pi by k, okay, and this is 3 pi by k. Okay, pi by k, this will be pi by k. Okay, coordinate pi by k. This is pi by k minus, this is omega into t. Okay, so let me simplify what we get. See 0.5 c divided cb0 divided by square root of 2 here. This I and j, I cross I will give you 0. So ij will give you k. I cross j will give you k. So this is k cap. Okay. And this part, you look, cos of pi minus omega t. Okay. Let me find out what is F2 then. F2 will be 2 pi coulomb into 0.5 C I cap cross B0 I plus J by root over 2 cos of, this will be 3 pi. So this, since it is see kz 3 pi by k, so it will be 3 pi minus omega t. You can directly write this thing. Okay. Now we have to take the ratio and see, this is magnitude. I can write, see, Ij here. Also this part, if you look, this I j, both are I j only, so that will be k. So 0.5 C B0 k cap by root 2 into this 2 pi will be there in front. Okay, 2 pi, and this is cos of 3 pi minus omega t. Actually pi and 3 pi phase wise, actually they are same. Okay, so what I can get from here, if I take the ratio, so this 3 pi and this pi, one is actually, so cos omega t pi minus c, so this is 3 pi, actually pi 1 pi, then if the particle was here at pi, then pi minus omega t means it is in the second quadrant, and when you take 3 pi, so you will have to come here 3 times, and then it will be 3 pi minus omega t. So ultimately you will be at the same position. So you know what you have to do, if you just take the ratio, see this factor is actually same, this factor is practically same, and this part is phase term. Okay, they are also at the same phase. Okay, in fact, so what we will get, actually f1 by f2, if I take the mod, then I get 4 by 2. Actually this is 2 is to 1. Okay, so option C will be the correct answer for this question. Now let us go to the next problem. This problem is very interesting problem. The problem says, this is from modern physics, a free electron of 2.6 electron volt energy collides with hydrogen ion. So electron collides with hydrogen ion, and then hydrogen, okay, so this results in the formation of hydrogen atom in the first excited state and a photon released. So to, okay, so what is happening, one free electron with energy this much electron volt collides with hydrogen, and hydrogen goes to first excited states, and then one photon released. You have to find out the frequency of the emitted photon. So how to do that? See, the energy of first excited state of hydrogen atom is minus 3.4, as you know. Okay, first excited state. Okay, now loss of energy will be how much? Loss of energy, so loss of energy will be 2.6 minus of minus 3.4 electron volt. This is in electron volt. The whole thing will be in electron volt. This will be 6 electron volt. Okay. So, or we can actually, yeah, so we can find out now what is the photon emitted. If this is the loss of energy, so this will be actually converted into photon. So we know lambda will be hc by, so E actually energy is equal to hc by lambda. So from there I can write hc by energy in ev. Okay, so this is 6 ev. So this will give you in nanometer if we write. So let me, this is electron volt. So you know, if I write this as, this is actually electron volt nanometer. So this will give you actually nearly, sorry, this is nearly 206 nanometer, nearly 206 nanometer. So we have got the wavelength. Now we have to find out frequency of the emitted photon, that is C by lambda. Okay, so C is 3 into 10 to the power 8 meter, and this is 206 into 10 to the power minus 9 meter. Okay, then what we get? So we'll get here, so you'll get actually, see, we have 3 by 206 into 10 to the power 17 meter. Okay, so ultimately what we'll get, 1.45 into 10 to the power, this will be not this meter per second, per second. Actually this will be per second. Per second means hertz. This will be actually 10 to the power 15 hertz. Let me check here. Okay, so we don't have any options like that. We'll just cross check. We have 10 to the power minus 9, 8 meter. Okay, 17, 18, 17, fine. Okay, so let me cross it. Okay, we have megahertz over here. Okay, so all the options are in megahertz. Okay, so megahertz, we can make it megahertz here. 1.45 into 10 to the power 6 into 10 to the power 9 hertz. Sorry, 9 hertz. 10 to the power 9 hertz. So that will give you megahertz, right? So 10 to the power 6 is megahertz. So I'll get from here, this 6 you just erase, so I'll get this megahertz. Okay, so these are all in megahertz, you can see that. So option B will be the correct answer for this question. Okay, so okay, now we'll have a analytical question over here. So a coil is placed in a magnetic field shown below. So the B is the magnetic field. A current is induced in the coil because B is okay. So you can see this is the induced current direction. So the induced current is in the anti-clockwise direction, as you can see here. So always what will happen, induced current, this induced current will actually induce a magnetic field also. Okay, that induced magnetic field will actually oppose the change in the flux, oppose the change in the flux. So in this case, we have to see what out of this four option is matching with the direction of induced current. So first option says magnetic field is outward and decreasing with time. Outward means it is out of the plane of the paper. Okay, so if it is out of the plane of the paper and decreasing, that means the flux linked in this coil will be decreasing, and that is inducing the current. Excuse me. See, induced current can be either due to decrease in the flux or increase in the flux. If the flux is constant, there is no induced EMF or induced current. So in this case, see, the magnetic field, if that decreases, then the flux also will decrease. If the flux decreases, then induced current will be induced in the coil, and the direction of the current will be in such a way that it will oppose the change in the flux. So change in the flux is actually here decreasing flux. So flux is decreasing. So what this induced current will do, it will try to increase the flux. So the direction of the induced magnetic field will be in the direction of B. So look, the induced current has to be in the direction C. The induced current will be in such a way that the induced magnetic field will be actually supporting, but that will be in the direction of the original magnetic field itself. So outward and decreasing, this is actually correct. Let us therefore see the other options also. The option B is saying parallel to the plane of the coil. If B is parallel to the plane of the coil, then there is actually no flux at all. Flux will be zero in that case. Okay, flux has to go or pass through the area. Okay, so this is not true. Parallel to the plane of the coil, increasing parallel is actually whenever there is a parallel direction, so no point of having flux actually. So that has to be perpendicular anyway, perpendicular to the plane of the loop. And outward and increasing, if it is increasing, then B should have been in the opposite direction, induced magnetic field. So this is also not true. Okay, so according to the induced current direction, the magnetic field will be outward, that is coming out of the plane of the paper, and it is decreasing. If it is increasing, then the induced current will be in the opposite direction, clockwise direction, so that the induced magnetic field will be reducing the cause or opposing the cause. Okay, so this is the answer. So what is the answer then? Answer will be the first option. Okay, the next problem is statement. Okay, let us see. So there are two statements, we have to check which one is correct, whether both are correct or any one is correct or both are true, sorry, both are wrong or false. That we have to cross check. So the first statement is saying that to get steady DC output from pulsating voltage received from full wave rectifier, we connect a capacitor across the output parallel to the load resistor. This is actually talking about full wave rectifier. Okay, full wave rectifier. Okay, about the circuit it is saying, see, in full wave rectifier, how do you get the output? You get output like this. Each half cycle you get like this, isn't it? This is called pulsating DC voltage. Okay, so you don't see anything going in the opposite phase or opposite direction. It is in the same direction, but still it is having a variation. Okay, having a variation, but actual DC is this one. Okay, the actual DC is this one. This is called pulsating DC. Pulsating DC. Okay, so from pulsating DC you have to get a steady value, steady DC output. So for that, actually, after the full wave rectifier circuit, you have to have a small filter circuit. Okay, here the statement is about the filter circuit. Filter circuit can be with a capacitor. Okay, so this is the first statement. To get a steady DC output from the pulsating voltage received from the full wave rectifier, we can connect a capacitor across the output parallel to RL, the load resistor. The second statement is saying that to get a steady output from the pulsating voltage received from a full wave rectifier, we can connect an inductor in series with load resistor. In the light of the above statements, choose the most appropriate answer from the options given below. So the option A is saying statement 1 is false, but statement 2 is true. Statement 1 is true, but statement 2 is false. So statement 1 is saying that you have to use a capacitor to get steady DC value from the pulsating output, and how you connect the capacitor, that is parallel to the load resistor. In the second case, it is said that you have to use an inductor, and that inductor you have to connect with the load resistor in series. Okay, actually both the statements are true. Either you can use a capacitor to get steady DC value from the pulsating DC output of the full wave rectifier, or you can use an inductor in series of the load resistor to get the same DC steady DC output. Let me show you the figure. So here actually both the statement 1 and 2 are correct. So option C will be the correct answer. Let me show you the filter circuit with inductor. So this is actually filter inductor. Look this is in series. Okay, inductor in series. Okay, inductor in series with load resistor. Okay, this is actually the full wave rectifier, FWR, full wave rectifier. Okay, and this is the filter circuit. Filter circuit. So you look, this circuit diagrams are very important in case of full wave and half wave rectifier. In fact, in any topics related to electronics and devices, the circuit diagram is very important. So this is one example of that. Okay, so how important this circuit diagram was. Okay, now I'll show you the filter circuit with capacitor. You can see that. Let me bring it little bit upper. Hope you are seeing now. I hope you are able to see this. See, this is the filter circuit here. So this is filter circuit here. Okay. So what is this? This is the capacitor. How is it connected with the load? It is connected in parallel connection with the load resistor. Okay. So this is how the full wave rectifier output, pulsating output, can be filtered to get a steady DC output. Okay. So these two circuits were important. Now we have got another question from current and moving current and moving charges and magnetic field, okay, or magnetism. Moving charges and magnetism. So you look this question. The question says a current of 1.5 ampere is flowing through a triangle of side 9 centimeter each. So these are all 9 centimeter. That means it is an equilateral triangle. The magnetic field at the centroid of the triangle is, so this figure was not given in the problem. Actually, to visualize, we needed a figure, so I have added here. So the magnetic field at the centroid of the triangle you have to find out. So you know you have to apply here Biot-Savart's law for Biot-Savart. Sorry. Biot-Savart law for finite current carrying wire. Okay, current carrying conductor. Finite conductor. Okay, or finite wire. So what is the formula for the magnetic field? Magnetic field will be given by mu0 I by 4 pi A or R, whatever you say, into sine theta 1 plus sine theta 2. This is the problem. See here, you know the sine theta 1 and sine theta 2 are what? So in this case, I'm just taking, see, I have 3 wire and each of them are, okay. So I think somehow this direction is wrong. Okay, I think this, let me just clean this. This direction is wrong. Actually, this is same conductor in the form of triangle, so better to correct it here. Okay, this will be in this direction. Okay, so what will be the magnetic field? See, if you see, according to the thumb rule, right hand thumb rule, the magnetic field will be always into the plane of the paper. Okay, into the plane of the paper. So it is actually inside the plane of the triangle. Okay, so that is fine. Now we have to find out the magnitude using this formula. So I'm taking this, let us say this is PQ. Okay, this ABC there. Okay, so ABC, let us say. This is A, B, and C. So BC wire I'm taking, BC wire. So this is finite in length. You can see that the length is L, and that is 9 centimeter here. We'll put the values later. And see, I need to find out magnetic field at this point. This is the centroid. So I need to find out what is the distance from this wire. So this A is actually R here. The distance from the wire, in fact, the perpendicular distance from the wire where the magnetic field has to be calculated due to this current carrying conductor. So you look here, this is actually perpendicular, okay? And if you draw perpendicular bisector and just add these two lines, okay? So the B and this, suppose this is actually P, this BP and CP, you will get again this this individual triangles. If you look, this is 60 degree, sorry, this is 30 degree, this is 90 degrees, so this will be 60 degree. Similarly, this will be 60 degree, this will be 90 degree, this is 30 degree. So theta 1 and theta 2 actually are same from the figure. Okay, so what are the angles? So I have got, so these angles are actually same. Okay, so from the point, see, this is 60 degrees. Okay, this is 60 degrees. Okay, so theta 1 and theta 2, these are actually 60 degrees. So I can write magnetic field for the BC wire mu0 I by 4 pi r, and this I can write as 2 into sine 60 degree. Sine 60 degree. So 60 degree means root 3 by 2. Root 3 by 2. Okay, so this two I can strike out. So I get root over 3 mu naught I by 4 pi r. Now I have to find out what is r. R is actually, see, if I just draw this perpendicular bisector, will be actually the height. Okay, perpendicular bisector of this angle A will be the height, and height, for a like equilateral triangle, we know root 3 by 2 into A. Okay, root 3 by 2 into A, let us say that is L here. So I'll get the whole height, okay, and this height will be actually divided as 2:1 ratio. This I have to multiply 1 over 3. So what I'll get L by 2 root over 3. This will be the R. Okay, so let me go to the next page and show you here. So what I get, magnetic field for this particular BC wire. So this is B, this is C. C. So mu0 I by 4 pi, in place of R, what I should write? I should write L by 2 root 3. Here I have 1 root over 3, and here L by 2 root 3. So 2 root 3 I can just multiply here. Okay, now see, this L is how much? 9 centimeter. So this root 3 they will make you 3 here. 6 into mu0 I by 4 pi into this is 9 into 10 to the power minus 2. Okay, -2 meter. And see, now the total magnetic field will be 3 into that, 3 into 6 into mu 0 I by 4 pi into 9 into 10 to the -2. Now look here, I is given. I is how much? 1.5 ampere. So 3 into 6 into mu 0 4 pi 4 pi into 10 to the power -7 mu 0 means I is 1.5 divided by 4 pi into 9 into 10 to the power -2. So you look, this 4 pi cancels each other. If I take this and this will be 9, so this 9 cancels out, and you know what we get? We get 3 into 10 to the power -5 Tesla. So let's check whether we have something. Yes, we have. So we have option C, and see, this will be inside the plane of the paper, so it will go into the plane of the triangle. So option C will be the correct answer for this question. Okay. All right. So we'll go to the next problem. This is again an analytical question. What is this question saying? Choose the incorrect statement. First statement is the electric lines of force, that means electric field lines, okay, entering into a Gaussian surface provide negative flux. Okay. If suppose this is a surface, Gaussian surface, so when it enters into, then it gives negative flux. Actually, this is a convention that we should take it positive flux when entering, and while going out we should take negative flux. Okay, so this is not true then. A charge q is placed at this, I'm sorry, this is, I think this is true. We have to find out the answer here. Choose the incorrect statement. Okay, we have to find out incorrect statement. No, actually this is yeah, so let me tell you here. The electric field lines entering into a Gaussian surface, this is actually convention to take this as negative. I'm sorry, this is negative and this is positive. While going out this is positive, while entering this is negative. Okay, or either way you can take, either positive or negative. So yeah, so here this statement seems to be correct. That a charge q is placed. So see, this is the silly mistakes we do in general. We have to check what statement we have to find out. We have to find out the incorrect statement. A charge q is placed at the center of the cube. See, I have a cube like this, and a charge is sitting at the center of the cube. The flux through all the faces will be the same. This is true. Through each faces it will be, if the flux is q by epsilon naught, then it will be 1/6 of this through each surface. This is equal. This is true. In a uniform electric field, net flux through a Gaussian surface containing no net charge is zero. This is also true. Suppose you have uniform electric field here, and you have a closed surface, Gaussian surface. Now see, the magnetic field lines are, sorry, electric field lines are coming, like entering and going out. Okay, so no net flux will be inside if there is no net charge inside. Okay, as I was saying, so according to see, by the first option itself we can verify this. If this is negative flux entering and going out positive flux, So ultimately, if you take the sum of these two, okay, going out and going in, okay, going in and like coming out, coming, see, since there is no charge inside, so all the flux will be passing through the surface. The number of flux lines or field lines entering are going out also. So that's why there will be no net flux inside the Gaussian surface. This is also true. When electric field is parallel to the Gaussian surface, it provides a finite non-zero flux. This is not true. Suppose I have a Gaussian surface like this, like this. Suppose this is in the XY plane. Okay, this is XY plane. Now, if your electric field is either uh, okay, in the XY plane, so suppose it is also your electric field line is actually parallel to this. That means, you know, the electric field lines are going like this. Okay, so this will be tangential, right? Tangential to the surface. So flux means the field line should pass across. Okay, so the surface has to be, at least the electric field line should have some component in the direction perpendicular to the Gaussian surface, so that you have some flux. So here this is actually not true. So option D, only option D will be incorrect over here. All right. So this was really a good question. Okay, so I'll clean everything. So option C is the correct answer for this question. Now I have another question. This is from electric current or electricity part. A resistor dissipates 192 joule of energy in 1 second. Okay, that means power is given per second. When a current 4 ampere is passed through it, so there is a resistor. When 4 ampere current is passing in 1 second, how much power or how much energy dissipated through this? This is Joule-Sitting law. Okay, Joule-Sit law. So that is given here. Now, when current is doubled, the amount of thermal energy dissipated in 5 seconds. So we can actually find out I square RT is the total heat energy, right? I square RT. If I just apply the first condition, so see, this is I square RT is equal to 192 joule. When my T is 1 second, I is 4, so R I can find out what is that. This is R is I square is 4 square into 1 second, so this will give you actually 12. Okay, 16, it will be 16 into 12 will be 192. So you'll get the resistance of the resistor. This is in ohm. Now you have to find out what is the power dissipated or energy dissipated in 5 seconds. Okay, let us say this is H prime I square RT, R and T. What is I now? I is now 8, double, right? 8 ampere. What is R? R is 12. What is this? T is actually 5 seconds. So I have 64 into 60. Okay, so 40 this much joule. Okay, so this will be 3840 joule. Okay, so let us go to the next problem. So this problem is again interesting. Let us see that. So in Young's double slit experiment, the slits are separated by 0.3 millimeter. Let me write down there. 0.3 millimeter. The screen is 5 meters away from the slits. So capital D is given as 1.5 meter. This I can write 3 into 10 to the power, sorry, 0.3 into 10 to the power minus 3, or let me write 3 into 10 to the power minus 4 meter. Okay. The distance between fourth bright fringes on both sides of the central bright fringe. See, generally, so the question says, see, suppose this is my central bright fringe. Okay, then you will have first like alternating. This is bright, so alternating dark, bright, dark, bright. You will have. So you are asked to see what is said. Distance between fourth bright fringes on both sides. See, bright. I'm just taking the bright one. So 1, 2, 3, 4. So here also 4. So the distance between them is actually given. See, this is given. I know the distance from this position, this one, I know. What is that? Yn is equal to n d lambda by small d. So if I write the fourth bright fringe, then the distance will be y fourth is equal to 4 d lambda by small d. Now I have to take the distance between these two. So this much is actually 4 d lambda by d. Okay. Then the distance between this fourth bright fringe from the both side, it will be actually 4 into 2. Okay, and this is given. So I have got, so according to the question, what is there given? The distance between fourth bright fringes from the both side of the central, on the both side of the central bright fringe is 24 centimeter. The frequency of the light used. So you have to find out the lambda first. So what is given? You have been given 2 into y fourth is equal to the given distance 24 centimeter, that is this much meter. Okay, so y fourth we know, right? So this will be then 8 d lambda, d and small d, this is small d, both are given here. This, so lambda will be 2.4 into 10 to the power minus 2 into d by 8 d lambda. So 2.4 into 10 to the power minus 2. What is d? Small d is actually 3 into 10 to the power minus 4 meter divided by 8. Sorry, this lambda I have to calculate. D is 1.5. Okay. So we'll have here, so this 0.5, this 0.5 I can strike them out. This will be 0.5, see 5 here, and this will be 3. So 3 by 5 into 10 to the power 6 meter. Now I have to find out the frequency. So I know frequency nu will be c by lambda. Lambda we have already got. C is 3 into 10 to the power 8 meter per second, and this is given as 3 by 5 into 10 to the power minus 6 meter. This will be per second. So look, this will be 5 into 10 to the power 14 per second is hertz. So this, see, the power is given already 14, so it will be 5. All right. So this was really an interesting problem. Let us go to the next problem. Here the question says a parallel plate capacitor of capacitance 200 microfarad is connected to a battery of 200 volt. So I have a parallel plate capacitor and it is air capacitor initially connected to a 200 volt DC battery, and it has C0 200 microfarad air capacitor initially. A dielectric slab of dielectric constant K is equal to 2 is now inserted into the space between the plates of the capacitor while the battery remain connected. So now I have just put a dielectric slab, and where K or epsilon R is dielectric constant K, you can say K or epsilon R, whatever you can say. So this is 2 given. The question is the change in the electrostatic energy in the capacitor. What we know, change in the electrostatic energy. Change in the electrostatic energy, I have to find out. So I know this will be half C V square minus half C0 V square. So what is C? C is actually C0 into K V square minus half C0 V square. Now half C0 V square into K minus 1. This K is 2 given, so this will be 1. So half C0 V square will be the change in the electrostatic energy. So how much is that? Half C0 is actually 200 microfarad. Okay, and V is 200 whole square. So I have here in joule, I have to find out, this will be in joule. So half I have, then I have 200, and this is 4 into 10 to the power minus 4 minus 4. Here we have already, sorry, this is plus 4. We have 10 to the power minus 6 over here. So these two and this 10 to the power 4 cancels with this, and this two cancel, so it will be actually 4 joule. Okay, 4 joule. So this will be 4 over here. I think this was the last question for this particular session. So we'll have few more questions from the 11th part from this particular paper. So next class, in the next class, I'll just complete this JEE main paper. Then we'll take up the JEE main papers for like from 2024. Okay, all the papers will take already two sessions of JEE mains exam is over. We'll take up all the questions from 2024. Okay, so for today we'll stop it here. Thank you for your patience. Bye.